There's a generalization of the spherical coordinates in n dimensions, and these are called hyperspherical coordinates. And this will be illustrated in the succeeding theorem. We can show that there exists a rotational invariant measure, say sigma n minus 1 on the Borel sets of the unit sphere, that is the boundary of the unit ball in Rn, and this is finite, such that the integral over Rn of some function g of x dx. So here g is either non-negative or Lebesgue integrable. This is equal to the following iterated integral, 0 to infinity and the integral over the unit sphere, GRS Rn minus 1 d sigma n minus 1 with respect to s dr. Okay, so you can think of Rns as follows. So R could be your length of your vector in Rn, and S would be your direction. So here, our direction is parameterized by a vector on the unit sphere. So it is normalized. So let us look at the proof of this theorem. We consider the following functions. First, let us define f from Rn into this Cartesian product. Again, this would be the length of your vector. This would be the direction of that vector. It is defined piecewisely. So this is following. So the length of this vector would be the norm, and the direction would be this one. So take note that this is a unit vector, the second component. So therefore, it lies on the unit sphere. So this is again the set of all vectors, let's say y in Rn with magnitude 1. This is piecewise, of course, if x is not 0. If x is 0, then we can say we can assign it arbitrarily to any point on the Cartesian product, so namely length 0, and y naught is a fixed element on the unit sphere. Example, you can take y naught to be the vector with all components 1, and you want to normalize this, so you divide by its norm, which is square root of n. This has an inverse, except at the single point. So here we define, let's say, this map onto Rn as follows. So you take the radius or the length, you have the direction, say y, this is r times y. Then you can see that if we take the composition at x, so this is h of f of x. So let us consider the case where x is not 0. So you have here the norm of x divided by this unit vector. The action of h is just multiplying the 2, which is equal to x. So this is the composition of h and f is the identity map except at the origin. Okay, so now let us consider or define two measures. Call it mu from the Borel sets corresponding to the lengths, and sigma n minus 1. So this is a finite measure, while mu can be infinite, as follows. So mu is a measure having density r to the n minus 1 dr. So you can think of this more precisely as d lambda 1r, where lambda 1 is the one-dimensional Lebesgue measure, and sigma n minus 1a is n times the n-dimensional Lebesgue measure of f inverse. So here we take radius less than 1, then take the Cartesian product with a. Of course, here must be a Borel set on the unit sphere. We claim that this with the f introduced above, namely this map, the associated image measure with respect to the n-dimensional Lebesgue measure is the same as the product measure of mu and a sigma n minus 1. So assuming at the moment that this claim holds, then let's consider this integral, this double or iterated integral, namely the one on the left-hand side of our theorem, or right-hand side of our theorem, this one. This, as we said, is basically the mu r. So therefore, I can write this as follows. So this is the integral okay, and write this in terms of a set. D mu r. And take note that Rs is the same as This is h of h of s. Or I should say h rs. Okay, so with this we now have the following. So this must be the composition of G and H R, S. According to Fubini's theorem, I can write this as a single integral. This would be the Cartesian product of the sets times the composition of G and H. Here I will now ignore the variables of integration. But the important part here is that we have the following product measure. According to our claim, this product measure is the same as this image measure. Our previous discussions allows us to write this as the integral of the composition of G, H, and F with respect to the Lebesgue measure. But this is identity almost everywhere. In fact, except at 0. So if that would be the case, this would be the integral. We now change this to Rn. That is the identity. Then you have G d lambda n. And of course, you can, if you want to emphasize the variable of integration, and then ignore lambda n, then you have this formula. So we have written the integral over Rn as an iterated integral. Here, the inner integral is over the unit sphere, corresponding to the directions. And the outer integral corresponds to the lengths. Okay, so to complete the proof, let us show our claim. So start with a positive R and an element A in the unit sphere, Borel sets of unit sphere. Then let's start with the image measure of this Cartesian product. And this is equal to, well, according to the definition of the image measure, F inverse 0R plus A. Now, you can show that this is the same as R times F inverse of the interval or the cell 0, 1 cross A. Now, since the second argument of F is invariant with respect to scaling. And you can prove this algebraically. So going back with the definition of F. So if you have an R here, a positive number, using the homogeneity of the Euclidean norm, you will have an R, and then that R will be cancelled. So scaling doesn't affect the second variable, so therefore you have this. However, it affects the first. So you have this, and we know that, okay, according to our formula for the scaling behavior of the Lebesgue measure, you have this. So you have a scale or a scalar r. So you should have n factors r with this Lebesgue measure. Okay, so going back with the definition of this. Okay, so this is almost sigma n minus 1, except that we need to multiply by n. So therefore, to compensate the missing factor, we need to divide by n. So take note that the measure of this is according to the definition of mu. It has a density r to the n minus 1, but since this is r, we use different variables, say s, d lambda 1 s. And since this is continuous, the Lebesgue integral is the same as the Riemann integral, and we know how to integrate this. This is basically s to the n over n from 0 to r. So we'll have r to the n over n. Hence, this is equal to mu 0r times sigma n minus 1a. Summarizing what we have discussed or what we have obtained. And from this, we apply the definition of the product measure. Now, to complete the proof, note that since the Cartesian product, these collections are positive, and the Borel sigma algebra on the unit sphere generates the product sigma algebra, namely this one, we have the claim, namely that this image measure coincides with the product measure on this Borel set and this Borel set on the unit sphere. And if you notice, this is the claim that we have mentioned a while ago. So if you want to be precise, here we have the product sigma algebra on this set and on this set, or on this Borel sigma algebra. So that completes the proof of our claim, and as we have discussed here, this will prove the desired equation stated by the theorem. Take note that this unit sphere is the boundary of the unit ball. And this inner integral is an example of what we call a boundary integral. So in the next lecture, we will discuss boundary integrals for general domains that are smooth enough.